For last few lectures, we are talking about image enhancement techniques, specifically the spatial domain techniques for image enhancement. So, for last few lectures, we have talked about the point processing techniques, and we have talked about few mask processing techniques for image enhancement. Both point processing techniques as well as mask processing techniques, we have said that they are spatial domain techniques in the sense that they work directly on the image pixels. So, among the mask processing techniques, what we have done so far is we have talked about the linear smoothing filters or averaging filters, and we have seen that this smoothing or averaging filters are some sort of integration operation which integrates the image pixels. We have also talked about a nonlinear filter or an filter based on order statistics, which we have said is the median filter, and we have talked about a sharpening filter, and we have said that this sharpening filter is nothing but some sort of differential operators which differentiate the image pixels to sharpen the image. And we have said that for such sharpening operation, the kind of derivatives which are most suitable is the second order derivative, and accordingly we have discussed about the second order derivative operators, which we have said as Laplacian operator, and we have demonstrated with results that how these Laplacian operators in the spatial domain, they try to enhance the content of an image. So, today we will talk about some more mask processing techniques, like we will talk about unsharp masking, we will talk about high boost filter, and we will also see that how the first order derivative operators can help in enhancement of image content, particularly at the discontinuities and edge regions of an image. And then we will go to our today's topic of discussion, which we say is the frequency domain techniques for image enhancement. And here again we will talk about various types of filtering operations like low pass filtering, high pass filtering, then equivalent to high boost filtering, and then finally we will talk about homomorphic filtering, and all these filtering operations will be in the frequency domain operations. So, let us first quickly see that what we have done in the last class. So, in the last class we have talked about the averaging filters or low pass filters, and we have talked about two types of spatial masks which are used for this averaging operation. One we have said as box filter, and we have said that in case of box filter, all the coefficients in the filter mask, they have the same value, and in this case all the coefficients have value equal to 1. The other type of mask that we have used is for weighted average operation, and here it shows the corresponding mask which gives the weighted averaging, and we have said that if you use this weighted average mask instead of the box filter mask, then what advantage we get is this weighted average mask tries to retain the sharpness of the image or contrast of the image as much as possible, whereas if we simply use the box filter, then the image gets blurred too much. Then these are the different kinds of results that we have obtained. Here the result is shown for an image which is on the top left. On the top right, the image is averaged by a 3x3 box filter. On the bottom left, this is an averaging over 5x5 filter, and on the bottom right, this is an image with averaging over 7x7 filter. And as it is quite obvious from these results that as we take the average or smooth out the image with the help of these box filters, the images get more and more blurred. Similar such results are also obtained, and as has been shown in this particular case, here also you find that using the low pass filter, the content, the noise in the image gets removed, but at the cost of the sharpness of the image. That is, when we take the average over a larger mask, a larger size mask, then it helps to reduce the noise, but at the same time a larger mask introduced large amount of blurring in the original image. So, there we have said that instead of using simple box filter or the simple averaging filter, if we go for order statistics, go for filtering based on order statistics like median filter, where the pixel value at a particular location in the processed image will be the median of the pixels in the neighborhood of the corresponding location in the original image. In that case, this kind of filtering also reduces the noise, but at the same time it tries to maintain the contrast of the image. So, here we have shown one such result. On the top left is the original noisy image. On the top right is the image which is obtained using the box filter, and the bottom image is the image which is obtained using the median filter. And here it is quite obvious that when we go for the median filtering operation, the median filtering reduces the noise, but at the same time it maintains the sharpness of the image. Whereas, if we go for box filtering of higher dimension, of higher size, then the noise is reduced, but at the same time the image sharpness is also reduced. That means, the image gets blurred. This is another set of results where you find that if you compare the similar result that we have shown earlier using the median filter, the noise is almost removed, but at the same time the contrast of the image is also maintained. So, this is the advantage of the median filter that we get, that in addition to removal of noise, you can maintain the contrast of the image. But this kind of median filtering, as we have mentioned, that this is very suitable for a particular kind of noise, removal of a particular kind of noise, which we have said the salt and pepper noise. The name comes because of the appearance of these noises in the given image. Then this shows another median filter output result. The bottom two images, on the left side it is the image obtained using the box filter, on the right hand side it is the image obtained using the median filter. The enhancement using the median filter over the box filter is quite obvious from this particular image. Then we have said that for enhancement operation we use the second order derivatives, and the kind of mask that we have used for second order derivative is the Laplacian mask. And for the Laplacian mask, these are the two different masks which we have used for the Laplacian operation. We can also use another type of masks where the center coefficients are positive. You find in case of earlier masks, the center coefficients are negative, whereas all the neighboring coefficients are positive in the Laplacian mask. In this case, the center coefficient is positive, whereas all other neighboring coefficients are negative. Now, using this Laplacian mask, we can find out the high frequency or detailed contents of an image, as has been shown in this particular one. Here you find that the original image, when it is processed using the Laplacian mask, the details of the image are obtained. On the left hand side, bottom left, we have shown the details of the image. On the bottom right, what we have done is, it is the same image which is displayed after scaling, so that the details are displayed properly on the screen. Now, here what has been done is, we have just shown the details of the image, but in many applications what is needed is, if this detailed information is superimposed on the original image, then it is better for visualization. So, these detailed images are to be added to the original image, so that we can get an enhanced image. So, the next one shows that if we have this original image, these are the same detailed images that we have shown earlier. On the right bottom, you have the enhanced image, where the detailed images are added to the original image. And for performing this operation, we can have a composite mask, where the composite mask is given like this. Here you find on the center pixel, we have the center coefficient of the mask is equal to 5, whereas you recollect that in case of Laplacian mask, the center pixel of the corresponding mask was equal to 4. So, if I change from 4 to 5, that means f x y value, the original image is going to be added with the detailed image to give us the enhanced images. So, that is what is done by using this composite mask. And this is the result that we obtain using the composite mask, similar to the one that we have shown earlier. You find that on the top we have the original image, and on the bottom right we have the enhanced image. Bottom left is an enhanced image when we use a mask where only the horizontal and the vertical neighbors are non-zero values, whereas the bottom right is obtained using the mask where we consider both the horizontal, vertical and diagonal coefficients to be non-zero values. And as it is quite clear from this particular result, that when we go for this kind of mask having both horizontal, vertical and the diagonal components as non-zero values, the enhancement is much more. Now, today we will talk about some more spatial domain or mask operations. The first one that we will talk about is called an unsharp masking. So, by unsharp masking we mean, you know that for many years the publishing companies were using a kind of enhancement where the enhancement in the image was obtained by subtracting a blurred version of the image from the original image. So, in such cases the sharpened image was obtained as f s x y. If I represent it by f s as the sharpened image, then this was obtained by subtracting f x y and f bar x y. So, this f bar x y is nothing but a blurred version or blurred f x y. So, if we subtract the blurred image from the original image, what we get is the details in the image, or we get a sharpened image. So, this f s x y is the sharpened image. And this kind of operation was known as unsharp masking. Now, we can slightly modify this particular equation to get an expression for another kind of masking operation, which is known as high boost filtering. So, high boost filtering is nothing but a modification of this unsharp masking operation. So, we obtain high boost filtering as, we can write it in this form, f h b x y, which is nothing but a times f x y minus f bar x y for a greater than or equal to 1. So, you find that if I set the value of this constant a equal to 1, then this high boost filtering becomes same as unsharp masking. Now, I can rewrite this particular expression. I can rewrite this in the form a minus 1 f x y plus f x y minus f bar x y. Now, this f x y minus f bar x y, this is nothing but the sharpened image f s x y. So, the expression that I finally get for high boost filtering is f b h b x y is equal to a minus 1 f x y plus f s x y. Now, it does not matter in which way we obtain the sharpened image. So, if I use the Laplacian operator to obtain this sharpened image, in that case the high boost filtered output f h b x y simply becomes a f x y minus the Laplacian operator on f x y, and this is the case when the center coefficient in the Laplacian mask will be negative. Or I will have the same expression which is written in the form a f x y plus Laplacian of f x y when the center coefficient in the Laplacian mask is equal to positive. So, as we have seen earlier that this first expression will be used if the center coefficient in the Laplacian mask is negative, and this second expression will be used if the center coefficient in the Laplacian mask is positive. So, using this we can get a similar type of mask where the mask is given by this particular expression. So, using these masks we can go for high boost filtering operation, and if I use this high boost filtering, I get the high boost output as we have already seen earlier. Now, so far the kind of derivative operators that we have used for sharpening operation, all of them are second order derivative operators. We have not used first order derivative operators for filtering so far, but first order derivative operators are also capable of enhancing the content of the image, particularly at discontinuities and at region boundaries or edges. Now, the way we obtain the first order derivative of a particular image is like this. What you use for obtaining the first order derivative is by using the gradient operator, where the gradient operator is given like this. Gradient of a function f, as the gradient is a vector, so we will write as a vector, is nothing but del f del x and del f del y. So, this is what gives the gradient of a function f. And what we are concerned about for enhancement is the magnitude of the gradient. So, magnitude of the gradient we will write it as del f, which is nothing but magnitude of the vector grad f, which is usually del f by del x square plus del f by del y square and square root of this. But you find that this particular expression, if I use, this leads to some computational difficulty, in the sense that we have to go for squaring and then square root, and getting an square root in the digital domain is not an easy task. So, what we do is we go for an approximation of this, and the approximation is obtained as del f del x magnitude plus del f del y magnitude of this. So, this is what gives us the first order derivative operator on an image. And if I want to obtain del f del x, you find that this del f del x can simply be computed as f x plus 1 y minus 1 plus f x plus 1 y plus 1 plus 2 f x x plus 1 y minus f x minus 1 y minus 1 plus f x minus 1 y plus 1 plus 2 f x minus 1 y. So, this is the first order derivative along x direction, and in the same manner we can also obtain the first order derivative in the y direction. Now, once we have this kind of discrete formulation of the first order derivative. So, similarly, I can find out del f del y, which will also have a similar form. So, once I have such discrete formulations of the first order derivatives, we can have a mask which will compute the first order derivative of an image. So, for computing the first order derivative along x direction, the left hand side shows the mask, and for computing the first order derivative along y direction, the right hand side shows the mask. And later on we will see that these operators are known as Chauvel operators. And using these first order derivatives, when we apply these first order derivatives on the images, the kind of processed image that we get is like this. So, you find that on the left hand side we have the original image, and on the right hand side we have the processed image, and in this case you find that this processed image is an image which highlights the edge regions or discontinuity regions in the original image. Now, in many practical applications, such simple derivative operators are not sufficient. So, in such cases what we may have to do is we may have to go for combinations of various types of operators which gives us the enhanced image. So, with this we come to the end of our discussion on spatial domain processing techniques. Now, we start discussion on the frequency domain processing techniques. Now, so far you must have noticed that these mask operations of the spatial domain operations using the masks, whatever we have done, that is nothing but a convolution operation in 2 dimension. So, what we have done is we have the original image f x y, we define a mask corresponding to the type of operation that we want to perform on the original image f x y, and using this mask, the kind of operation that is done, the mathematical expression of this is given on the bottom, and if you analyze this, you will find that this is nothing but a convolution operation. So, using this convolution operation, we are going for spatial domain processing of the images. Now, we have already seen during our earlier discussions that a convolution operation in the spatial domain is equivalent to multiplication in the frequency domain. Convolution in the spatial domain is equivalent to multiplication in the frequency domain. Similarly, a convolution in the frequency domain is equivalent to multiplication in the spatial domain. So, what we have seen is that if we have a convolution of say 2 functions f x y and h x y in the spatial domain, the corresponding operation in the frequency domain is multiplication of f u v and h u v, where f u v is the Fourier transform of this spatial domain function f x y and h u v is the Fourier transform of the spatial domain function h x y. Similarly, if we multiply 2 functions f x y and h x y in the spatial domain, the corresponding operation in the frequency domain is the convolution operation of the Fourier transforms of f x y, which is f u v, that has to be convolved with h u v. So, these are the convolution theorems that we have done during our previous discussions. So, to perform this convolution operation, the equivalent operation can also be done in the frequency domain if I take the Fourier transform of the image f x y and I take the Fourier transform of the spatial mask, that is h x y. So, the Fourier transform of the spatial mask h x y, as we have said that this is nothing but h u v in this particular case. So, the equivalent filtering operations we can do in the frequency domain by choosing the proper filter HUV, then after taking the product of FUV and HUV, if I take the inverse Fourier transform, then I will get the processed image in the spatial domain. Now, to analyze this further, what we will do is, we will take the cases in one dimension and we will consider the filters based on Gaussian functions for analysis purpose. The reasons we are choosing these filters based on Gaussian function is that the shapes of such functions can be easily specified and easily analyzed. Not only that, the forward transformation, the forward Fourier transformation and the inverse Fourier transformation of Gaussian functions are also Gaussian. So, if I take a Gaussian filter in the frequency domain, I will write a Gaussian filter in the frequency domain as H u is equal to some constant a e to the power minus u square by 2 sigma square, where sigma is the standard deviation of the Gaussian function. And if I take the inverse Fourier transform of this, then the corresponding filter in the spatial domain will be given by H x is equal to root over 2 pi a e to the power minus 2 pi square sigma square x square. Now, if you analyze these two functions, that is H u in the frequency domain and H x in the spatial domain, you find that both these functions are Gaussian as well as real. And not only that, both these functions, they behave reciprocally with each other. That means, when H u has a broad profile, this particular function H u in the frequency domain, it has a broad profile, that is, it has a large value of standard deviation sigma. The corresponding H x in the spatial domain will have a narrow profile. Similarly, if H u has a narrow profile, H x will have a broad profile. Particularly, when the sigma tends to infinity, then this function H u, this tends to be a flat function, and in such case the corresponding spatial domain filter H x, this tends to be an impulse function. So, this shows that both H u and H x, they are reciprocal to each other. Now, let us see what will be the nature of these functions, nature of such low pass filter functions. So, here on the left hand side, we have shown the frequency domain filter H u as a function of u, and on the right hand side, we have shown the corresponding spatial domain filter H x, which is a function of x. Now, from these filters, it is quite obvious that all the values, once I specify a filter H u as a function of u in the frequency domain, the corresponding filter H x in the spatial domain, they will have all positive values. That is, none H x never becomes positive negative for any value of x. And the narrower the frequency domain filter, more it will attenuate the low pass frequency components, resulting in more blurring effect. And if I say make the frequency domain filter narrower, that means the corresponding spatial domain filter or spatial domain mask will be flatter. That means the mask size in the spatial domain will be larger. So, this slide shows two such masks that we have already discussed during our previous discussion. So, this is a mask where all the coefficients are positive and same, and in this mask the coefficients are all positive, but the variation shows that it is having some sort of Gaussian distribution in nature. And we have already said that if the frequency domain filter becomes very narrow, it will attenuate even the low frequency components, leading to a blurring effect of the processed image. Correspondingly, in the correspondingly in the spatial domain, the mask size will be larger, and we have seen through our results that if I use a larger mask size for smoothing operation, then the image gets more and more blurred. Now, in the same manner as we have said the low pass filter, we can also make the high pass filters again in the Gaussian domain. So, in this case, in case of Gaussian domain, using the Gaussian function, a high pass filter H u can be defined as a into 1 minus e to the power minus u square by 2 sigma square. So, this is the high pass filter which is defined using the Gaussian function. If I take the inverse Fourier transform of this, the corresponding spatial domain filter will be given by h x equal to a into delta x minus the same square root of 2 pi into a into e to the power minus 2 pi square sigma square x square. So, if I plot this in the frequency domain, this shows the high pass filter in the frequency domain. So, as it is quite obvious from this plot that it will attenuate the low frequency components, whereas it will pass the high frequency components, and the corresponding filter in the spatial domain is having this form, which is given by h x as a function of x. Now, as you note from this particular figure, from this particular function h x, that h x can assume both positive as well as negative values. And an important point to note over here is, once h x becomes negative, it will remain negative, it does not become positive anymore. And in the spatial domain, the Laplacian operator that we have used earlier, the Laplacian operator was of similar nature. So, the Laplacian mask that we have used, we have seen that the center pixel is having a positive value, whereas all the neighboring pixels have the negative values. And this is true for both the Laplacian masks, if I consider only the vertical and horizontal components, or whether along with vertical and horizontal components, I also consider the diagonal components. So, these are the two Laplacian masks where the center coefficient is positive and the neighboring coefficients, once they become negative, they will remain negative. So, this shows that using the Laplacian mask in the spatial domain, the kind of operation that we have done is basically a high pass filtering operation. So, now first of all, we will consider the smoothing frequency domain filters or low pass filters in the frequency domain. Now, as we have already discussed that edges as well as sharp transitions like noises, they lead to high frequency components in the image. And if we want to reduce these high frequency components, then the kind of filter that we have to use is a low pass filter, where the low pass filter will allow the low frequency components of the input image to be passed to the output, and it will cut off the high frequency components of the input image, which will not be passed to the output. So, our basic model for this filtering operation will be like this, that we will have the output in the frequency domain, which is given by G u v, which is equal to H u v multiplied by F u v, where this F u v is the Fourier transform of the input image, and we have to select a proper filter function H u v, which will attenuate the high frequency components, and it will let the low frequency components to be passed to the output. Now, here we will consider an ideal low pass filter, where we will assume the ideal low pass filter to be like this, that H u v is equal to 1 if d u v, where d u v is the distance of the point u v in the frequency domain from the origin of the frequency rectangle. So, if d u v is less than or equal to some value, say d 0, then h u v will be equal to 1, and this will be equal to 0 if the distance from the origin of the point u v is greater than d 0. So, this clearly means that if I multiply f u v with such an h u v, then all the frequency components lying within a circle of radius d 0 will be passed to the output, and all the frequency components lying outside this circle of radius d 0 will not be allowed to be passed to the output. Now, if the Fourier transform f u v is centered is the centered Fourier transform, that means the origin of the Fourier transform rectangle is set at the middle of the rectangle, then this d u v, the distance value, is simply computed as u minus m by 2 square plus v minus n by 2 square root of this, where we are assuming that we have an image of size m by n. So, for an m by n image size, d u v will be computed like this if the Fourier transform f u v is the centered Fourier transformation. A plot of this kind of function is like this. So, here you find that the left hand side shows the perspective plot of such an ideal filter, whereas on the right hand side we just show the cross section of such an ideal filter. And in such cases, we define a cutoff frequency of the filter to be the point of transition between h u v equal to 1 and h u v equal to 0. So, in this particular case, this point of transition is the value d 0. So, we consider d 0 to be the cutoff frequency of this particular filter. Now, it may be noted that such a sharp cutoff filter is not realizable using the electronic components. However, using software, using computer program, it is different, because we are just letting some values to be passed to the output and we are making the other values to be 0. So, this kind of ideal low pass filter can be implemented using software, whereas using electronic components we are not able to implement such ideal low pass filters. So, a better approximation of this is a filter which is called a Butterworth filter. So, a Butterworth filter or Butterworth low pass filter is the response, the frequency response of this is given by h u v is equal to 1 upon 1 plus d u v by d 0 to the power 2 n. So, this is a Butterworth filter of order n. The response of the plot of such a Butterworth filter is shown here. So, here we have shown the Butterworth filter, the perspective plot of the Butterworth filter, and on the right hand side we have shown the cross section of this Butterworth filter. Now, if I apply the ideal low pass filter and the Butterworth filter on an image, let us see what will be the kind of the output image that we will get. So, in all these cases we assume that first we take the Fourier transform of the image, then multiply that Fourier transformation with the frequency response of the filters, then whatever the product that we get, we take the inverse Fourier transformation of this to obtain our processed image in the spatial domain. So, here we use two images for test purpose. On the left hand side, we have shown an image without any noise, and on the right hand side, we have shown an image where we have added some amount of noise. Then, if I process that image using the ideal low pass filter and using the Butterworth filter, the top row shows the results with ideal low pass filter when the image is without noise, and the bottom row shows the result by applying the Butterworth filter again when there is no noise contamination with the image. Here you find, as the top row shows, that if I use the ideal low pass filter for the same cutoff frequency say 10, the blurring of the image is very high compared to the blurring which is introduced by the Butterworth filter. If I increase the cutoff frequency, when I go for cutoff frequency of 20, in that case you find that in the original image, in the ideal low pass filtered image, the image is very sharp, but the disadvantage is that if you simply look at these locations, say along these locations, you find that there is some ringing effect. That means, there are a number of lines, undesired lines, which are not present in the original image. Same is the case over here. So, the Butterworth filter, Butterworth low pass filter, it introduces the ringing effect which are not visible in case of Butterworth filter. Now, the reason why the ideal low pass filters introduces the ringing effect is that we have seen that for an ideal low pass filter, in the frequency domain, the ideal low pass filter response was something like this. So, if I plot u versus h u, this was the response of the ideal low pass filter. Now, if I take the inverse Fourier transform of this, corresponding h x will have a function of this form, like this. So, here you find that there is a main component which is the central component, and there are other secondary components. Now, the spread of this main component is inversely proportional to d0, which is the cutoff frequency of the ideal filter, ideal low pass filter. So, as I reduce d0, this spread is going to increase, and that is what is responsible for more and more blurring effect of the smooth image. Whereas, all the secondary components, the number of these components again over an unit length is again an inverse function, inversely proportional to this cutoff frequency d0, and these are the ones which are responsible for ringing effect. When I use Butterworth filter, the outputs that we have shown here using the Butterworth filters, these outputs are obtained using Butterworth filter of order 1, that is value of n is equal to 1. So, Butterworth filter of order 1 does not lead to any kind of ringing effect, whereas if I go for Butterworth filter of higher order, that may lead to the ringing effect. In the same manner, we can also go for Gaussian low pass filter, and we have already said that for a Gaussian low pass filter, the filter response HUV is given by e to the power minus d square uv upon 2 sigma square, and if I allow sigma to be equal to the cutoff frequencies at d0, then this HUV, the filter response, will be e to the power minus d square uv upon 2 d naught square. Now, if I use such a Gaussian low pass filter for filtering operation, and as we have already said, the inverse Fourier transform of this is also Gaussian in nature. So, using the Gaussian filters, we will never have any ringing effect in the processed image. So, this is the kind of the low pass filtering operation or smoothing operations in the spatial domain that we can have. We can also have the high frequency operation or sharpening filters in the frequency domain. So, as low pass filters give the smoothing effect, the sharpening effect is given by the high pass filter. Again, we can have the ideal high pass filter, we can have the Butterworth high pass filter, we can also have the Gaussian high pass filter. So, just in the reverse way, we can define an ideal high pass filter as, for an high pass filter, the ideal high pass filter will be simply H u v is equal to 0 if d u v is less than or equal to d 0, and this will be equal to 1 if d u v is greater than d 0. So, this is the ideal high pass filter. Similarly, we can have Butterworth high pass filter, where H u v will be given by the expression 1 upon 1 plus d 0 by d u v to the power 2n, and we can also have the Gaussian high pass filter, which is given by H u v is equal to 1 minus e to the power minus d square u v upon 2 d 0 square. And you find that in all these cases, the response, the frequency response of an high pass filter, if I write it as A H H p, is nothing but 1 minus the response of a low pass filter. So, the high pass filter response can be obtained by the low pass filter response, where the cutoff frequencies are same. Now, using such high pass filters, the kind of result that we can obtain is given here. So, this is the ideal high pass filter response, where the left hand side gives you the perspective plot and the right hand side gives you the cross section. This shows the Butterworth filter perspective plot as well as cross section of a Butterworth filter of order 1. And if I apply such high pass filters to the image, to the same image, then the result that we obtain is something like this. So, here on the left hand side, this is the response of an ideal high pass filter. On the right hand side, we have shown the response of a Butterworth high pass filter, and in both these cases the cutoff frequency was taken to be equal to 10. This one, where the cutoff frequency was taken to be equal to 50, and if you closely look at the ideal filter output, here again you find that you can obtain, you can find that there are ringing effects around this boundaries, whereas in case of Butterworth filter there is no ringing effect. And again we said that this is a Butterworth filter of order 1. If I go for higher order Butterworth filters, that also may lead to ringing effects. Whereas, if I go for a high pass filter which is Gaussian high pass filter, the Gaussian high pass filter does not lead to any ringing effect. So, using these high pass filters, I can go for smoothing operation. Using the low pass filters, I can go for the smoothing operation, and using the high pass filters, I can go for image sharpening operation. The same operation can also be done using the Laplacian in the frequency domain. It is simply because if I take the Laplacian of a function, if for a function f x y, I get the corresponding frequency domain, say f u v, the corresponding Fourier transform, then the Laplacian operator, if I perform del square f x y and take the Fourier transform of this will be nothing but, it can be shown, it will be equal to minus u square plus v square into f u v. So, using this operation, if I consider say h u v is equal to minus u square plus v square, and using this as a filter, I filter this f u v, and after that I compute the inverse Fourier transformation, then the output that we get is nothing but a Laplacian operated output, which will obviously be an enhanced output. Another kind of filtering that we have already done during in connection with our spatial domain operation, that is high boost filtering. So, there we have said that in spatial domain, the high boost filtering operation, the high boost filtering output f x y, if I represent this as f h b x y, is nothing but a into f x y minus f l p x y, and which is can be represented as a minus 1 into f x y plus f high pass filtered output x y. In the frequency domain, the corresponding operation, the corresponding filter can be represented by h b u v is equal to a minus 1 plus high pass filter u v. So, this is what is the high boost filter response in the frequency domain. So, if I apply this high boost filter to an image, the kind of result that we get is something like this, where again on the left hand side is the original image and on the right hand side it is the high boost filtered image. Now, let us consider another very interesting filter, which we call as homomorphic filter. Homomorphic filter. The idea aims from one of the earlier discussions, where we have said that the intensity at a particular point in the image is a product of two terms. One is the illumination term, other one is the reflectance term. That is f x y, we have earlier said that it can be represented by an illumination term I x y multiplied by R x y, where R x y is the reflectance term. Now, coming to the corresponding frequency domain, because this is a product of two terms, one is the illumination, other one is the reflectance, taking the Fourier transform directly on this product is not possible. So, what we do is, we define a function say z x y, which is logarithm of f x y, and this is nothing but logarithm of I x y plus logarithm of R x y. And if I compute the Fourier transform, then the Fourier transform of z x y will be represented by z u v, which will have two components, f I u v plus f R u v, where this f I u v is the Fourier transform of ln I x y and f R u v is the Fourier transform of ln or xy. Now, if I define a filter say HUV and apply this filter on this ZUV, then the output that I get is say SUV, which is equal to HUV times ZUV, which will be nothing but HUV times FIUV plus HUV times FRUV. Now, taking the inverse Fourier transform, I get Sxy is equal to I dash xy plus R dash xy. And finally, I get Gxy, which is nothing but e to the power Sxy, which is nothing but e to the power I dash xy into e to the power R dash xy, which is nothing but I 0 xy into R out xy. So, the first term is the illumination component and second term is the reflectance component. Now, because of this separation, it is possible to design a filter which can enhance the high frequency components and it can attenuate the low frequency components. Now, it is generally the case that in an image the illumination component leads to low frequency components because illumination is slowly varying, whereas the reflectance component leads to high frequency components, particularly at the boundaries of two reflecting objects. As a result, the reflectance term leads to high frequency components and illumination term leads to low frequency components. So, now if we define a filter like this, a filtered response like this, and here if I say that I will have say gamma H greater than 1 and gamma L less than 1, this will amplify all the high frequency components, that is the contribution of the reflectance, and it will attenuate the low frequency components, that is contribution due to the illumination. Now, using this type of filtering, the kind of result that we get is something like this. Here on the left hand side is the original image and on the right hand side is the enhanced image. And if you look in the boxes, you find that many of the details in the boxes which are not available in the original image is now available in the enhanced image. So, using such homomorphic filtering, we can even go for this kind of enhancement where the illumination, the contribution due to illumination will be reduced. So, even in the dark areas we can take out the details. So, with this we come to an end to our discussion on image enhancements. Now, let us go to some questions of our today's lecture. The first question is, a digital image contains an unwanted region of size 7 pixels. What should be the smoothing mask size to remove this region? Why Laplacian operator is normally used for image sharpening operation? Third question, what is unsharp masking? Fourth question, give a 3 by 3 mask for performing unsharp masking in a single pass through an image. Fifth, state some applications of first derivative in image processing. Then what is ringing? Why ideal low pass and high pass filters lead to ringing effects? How does blurring vary with cutoff frequency? Does Gaussian filter lead to ringing effect? Give the transfer function of a high boost filter, and what is the principle of homomorphic filter? Thank you.